So we have been looking so far at calculating energies, particularly I want to talk about Gibbs free energies, always using standard state conditions. So we're looking at things being at 1 atmosphere of pressure, or making sure that they are 1 molar if they are in solution, things of that sort, right? But what happens if we are not under standard conditions? If that's the case, we come up with a new equation. Delta G equals delta G0 plus RT ln Q, where Q is the equilibrium constant, not necessarily at equilibrium. All right, so under these conditions, I want to do a calculation for non-standard conditions of nitrogen and hydrogen. Again, if they were under standard conditions, they would all be 1 atmosphere. But I want to look at this equation at 298 Kelvin. I want to look at the pressure of the nitrogen and hydrogen gas being the same at 200 atmospheres, and then the pressure of the ammonia being at 50 atmospheres. So how do I go about doing this? Well, if delta G is equal to delta G0 plus RT ln Q, then the delta G is equal to delta G naught. We did that calculation a while back, and we said that delta G naught was negative 33.0 kilojoules, and that is for every, oops, is that right? No, that is not right. That should be minus 16.5 kilojoules per mole of ammonia. So it's negative 33 kilojoules for every 2 moles of ammonia. So I can still use that number, but I need to put a 2 down there. So it's delta G0 plus R, and you recall R is the gas law constant, 0.08206 liter atmospheres per mole Kelvin. But in this case, we don't want the liter atmospheres, we want joules. So R in this case is 8.314 joules per Kelvin mole. All right, so that's our R, and our T obviously is 298 Kelvin. And then we have to multiply that by the natural log of Q, and Q again is the concentration of the products divided by the reactants, or the pressure of the products divided by the reactants. So the products in this case was the ammonia, and the ammonia was at 50 atmospheres, and we're going to square that. Actually, I don't need the units in there at all because those units are essentially going to go away. So 50 squared divided by the reactants, and each of the reactants was 200, so it was 200 for the ammonia, and 200 for the nitrogen, and then it was also 200 for the hydrogen, but hydrogen needs to be cubed. So I end up with 50 squared divided by 200, actually to the 4th power. And if you do this reaction, you end up getting this whole last piece, the 8.314 and the 2.918. So I end up getting something like minus 16.5 kilojoules plus, and notice that 8.314 is in joules, so I'm going to want to convert that into kilojoules. And that all ends up working out to be a negative 33.1 kilojoules. And so that gives me a value of minus 49.6 kilojoules for that reaction under those conditions.